Morena, good morning. Um, this is Nirmal Nair, the General Chair for TENCON 2021 conference. We are on day 4. It's a Friday here in New Zealand, 10th of December at 9 a.m. So we come to the last day of this conference, this day-night conference. But today also I would like to welcome a new stream of audience, which is the workshop day. And so we have 2 fantastic workshops, one in the morning and one in the afternoon. Just for the benefit of those who are joining and those who have been with us for the past 3 days, some quick statistics on the conference first, and then later on I'll just talk a little bit about the workshop day as well. Welcome back, all those attendees who have been there with us for the past 3 days or so. So this is part of the TENCON 2021 conference, and it is part of IEEE. Just for the benefit of those who are joining today, IEEE was formed somewhere in 1966 as an amalgamation of two associations, American Institute of Electrical Engineers and Institute of Radio Engineers. And that became IEEE, and New Zealand has been part of that since then. But once it was formed, the Asia Pacific regions together, which we call it as Region 10, which today spans from Afghanistan in the west, Mongolia in the north, Japan to the east, and to New Zealand in the south, formed its root in 1968. New Zealand was one of the first inaugural countries, along with Japan, Pakistan, and I think it was Korea. So it has been about 52 years about the technologies which we see. But 52 years ago, it was power system and communication. But we have spanned many different technologies in the past 52 years or so. In the last 20 years or so, there has been an acceleration of these technologies. as we speak, and this conference is themed around that. Now, this Asia Pacific conference goes way back to 1980 when the first conference was held in Hong Kong, and New Zealand has never hosted it. So we thought to bring this conference here to New Zealand way back in 2019. IEEE presence in New Zealand has always been there for the past 50 years in subtle forms or the other. We just had one New Zealand entity in 1968. Today we have four. New Zealand North, centered around Auckland. New Zealand South, centered around Christchurch. And below, New Zealand Central, which is Wellington, and up to Waikato in the north. And we have a council as well. So together, leading IEEE New Zealand North led the bid in 2019 in the year of APEC. And that's why it was scheduled, but things changed dramatically, as you know, in the last couple of years. We were planning to initially do it fully live 2 years ago. And I would like to acknowledge all the help of Auckland Convention Bureau for making this happen, for the bid and the successful would get it through. But things changed with the COVID-19 variation, and then we thought we will go online, kind of live first. We waited up to 2021. We thought we'll go with blended format based, physically here in Auckland and physically here in New Zealand and online rest. And August 2021 changed everything, so we decided to go fully online. And we kind of blended it as a day-night conference kind of thing, and that's what we are here today. So just check out, for those who have joined, www.tencon, TENCON 2021.com. All the details are there, and all the handbook details are there of what has happened. So today is day 4. Welcome to day 4. So basically, we have 2 parallel sessions. So the papers, we have been streaming through 180 papers for the past couple of days. We were friendly to Asia Pacific people on our Tuesday and Wednesday, when we started at 2:30. But today, many of the other people might be sleeping, I think. But this is being streamed live, this is being recorded, so they'll be able to see this through. So with that introduction, I would just want to pass this over to the workshop part of it. So I would like to introduce Professor Neville Watson. So professor at University of Canterbury, and he's leading a multi-institutional strategic project called as Architecture of the Future Low Carbon Resilient Electrical Power System. This goes very well with the theme of our conference. If you look at our conference, we had a smarter, cleaner, secure, and resilient living. Now, the secure and resilient living, some of you might have noticed in the keynote, was around cybersecurity and things like that. But today's workshop kind of captures the first 2 parts, the smarter and the cleaner. The cleaner one is what I think fits well with the fan workshop. The smarter one would fit with the workshop this afternoon, which is the robotics workshop. And just watch out, there are some high school teams from New Zealand participating. There are some middle school participants and things like that. So this workshop day, once you're done with the morning, you can just join in the afternoon. So with that, I will pass it on to, I will want to bring on the stage Professor Neville Watson.
Thank you very much for that introduction, and much appreciated. So I was just going to spend a few minutes just giving a quick overview of the project, just so that those that aren't familiar will be informed about it, and that'll also lead into the speakers we have for the workshop. So as you can see, the full title is Architecture of the Future Low Carbon Resilient Electrical Power System, but that's a bit of a mouthful. So we've actually got a short form, and the short form is the Future Architecture of the Network, or FAN for short. So let's discuss exactly what we're talking about. So we know about in the 1880s, there was this fight over AC and DC, and eventually AC won, and particularly because it was easy to transform the voltage and to actually go up to higher voltage for transmission. But we're seeing a war against it in a way because of modern technology. And what is the center of it is power electronics. Power electronics now allows us to get many efficiencies in many ways with power electronic converters. And here's a slide of all the different things that go into the modern things. And as you'll see, a lot of them are actually involve renewable energy. We want to get clean energy into the system, whether it's solar or wind. And the enabling technology is power electronics. And at the heart of these is a DC. We have battery storage needed to overcome the intermittency of the energy sources. It's DC. If you have a look in your home, how many of your appliances now are inverter based? Because there's a lot of efficiencies gained by variable speed. Variable speed drives on compressors adds to the efficiency. So as we can see, the modern day landscape is going to DC. So that basically has motivated the project. And the real question is not whether DC conveyance will be used, but what is the role in the power system? How much should be DC and how fast should it be implemented? So the whole aim of this project is looking at a hybrid AC-DC system and looking at the transition to DC systems in the grid. How much should we use? So we're taking a new look at the system. Instead of patching it up and adding things and getting a more complicated system, we're saying, okay, where do we want to be in 2050? What is the optimum system? And this is basically the basis for this project. So this here is actually the diagram for it. So what basically we have a concept diagram, and as you see, if I can get the pointer working, you'll see a meshed HVDC system. So we've got HVDC, we've had it for many years in New Zealand. It's been a point-to-point. There's many benefits in making it meshed and having a big, strong HVDC mesh system. And the MV, DC, you've got DC trains, DC transportation, hydrogen production. At the medium voltage, there are many benefits for having DC, and at the LV level, low voltage level, running DC around the home. Now, the project isn't saying that everything's got to be changed to DC. We're saying that AC transformers are still the most efficient way for converting from one voltage to another. There's an optimum voltage for a given power level and distance. So we're always going to have to transform voltage levels. So part of the system is always going to be AC, but how much should be changed to DC? And that is really the thesis for the project. And as you can see, it's enabling EVs, battery storage, PV, as well as wind power. Now this project is actually split into work streams. So this shows 3 work streams. So the first work stream is looking at the architecture, developing the tools to look at the architecture. So the first one is dominated by simulation. The next one is looking at the different topologies for the DC network. And the third one is looking at the devices and topologies of the converters needed for it. The fourth is the transition path. And the fifth one is Vision Mataranga. So the next slide shows the 5 work stream, the work stream leaders, and some of the players in it, and the goals for it. Now, in terms of management for the project, we have an advisory board, which is made up of people from industry, which gives us feedback. We also have set up a science advisory board to help us, and these are international experts to give us feedback on the direction we're taking. And fan team there, as you can see, we've got both international and national collaborators, both in academia as well as in industry. So just the plan for what is coming up now, we have a set of speakers, international experts that are going to speak each on one of these themes. So WS1 stands for Workstream 1, 2, and 3. We'll have a break, and then we'll actually go over to the panel session where we actually interact and actually have questions being posed. So that basically is an outline, and I'd like to hand it over and give thanks to the TENCON organization for enabling us to have this workshop as part of their conference. So Thank you very much, and over to you.
Thanks, Neville, for that fantastic short and pithy discussion on the background. And I would like to acknowledge that for those of you, this is one of the largest strategic program investment which the country has made, and I would like to acknowledge Ministry of Business, Innovation and Employment, and a particular instrument called as SSIF. It's called as Strategic Science Investment Fund, and the call for proposals came last year, and this was selected as one of the 4 SSIF proposals. So a national team of experts are involved in this, and Professor Neville Watson is leading that. And we started just 1 year ago, and we are just setting the tone as we speak. And I think it's impressive to see that we have got some of the world experts in DC technologies in the areas which we are looking at, and also giving us helpful advice as we move ahead in this ambitious project for at least for New Zealand's case, but also the globe. So it's nice to see that. So how are we going to run this? I will. The whole program is going to be managed by Master of Ceremony. So here I would like to introduce Andrew Lapthorne. He is the finance chair for TENCON 2021, and also he happens to be one of the key part of the FAN project. So he will be taking you through the first half, as you can see, and then he would facilitate the panel, and then he would close off. And so from now onwards till about 11:45, he will run it through, and then I will come back later to kind of wrap up and thank on behalf of TENCON 2021. So ladies and gentlemen, it is FAN for you, and over to you, Andrew.
Thank you very much, Neville, for the introduction, and also thanks to Neville for the great overview of the FAN project. So on the agenda we have today, we've got a few pre-recorded talks from various people from around the world related to different work streams. So the first talk we're going to have is related towards work stream 1, the modelling work stream, and this is by Professor Ani Goli from the University of Manitoba. So Professor Goli is a distinguished professor and NSERC Industrial Chair in Power Systems Simulation at the Department of Electrical and Computer Engineering at the University of Manitoba. He has over 30 years experience in the development of modelling tools for power networks, incorporating power electronics equipment such as HVDC and fax converters. He is one of the original developers of the widely used PSCAD EMTDC simulation program and has made important contributions to the development of the world's first real-time digital simulator for power systems, the RTDS, from Winnipeg, Canada. Dr. Goli is a professional engineer in the province of Manitoba, fellow of the Canadian Academy of Engineering, and a fellow of the Institute of Electrical and Electronic Engineers for his contributions to modelling of flexible AC transmission systems. He received the IEEE Ngāi Hinagawari Fax Medal in 2007. So I'd like to have Professor Ani Goli's presentation.
Ladies and gentlemen, good morning. It's a pleasure for me to be speaking at this TENCON conference in 2021 in New Zealand. I'm Ani Goli from the University of Manitoba, and I will be talking on the simulation of hybrid AC-DC systems. Here's an outline of my talk. I'll firstly begin with a description of how the energy system has changed and how the modern energy network is different with its high reliance on power electronic converters and its use of renewable energy systems, and what challenges such a network creates for simulation, such as various time step requirements and different levels of accuracy. And I'll talk about solutions to some of these challenges on simulation, such as hybrid simulation and interfacing-based simulations. And finally, I'll conclude with some remarks. Just a few comments on the nature of the modern power grid. There's an increasing inclusion of renewable energy sources in the modern grid, and the supply is not also dispatchable anymore because these sources are not always reliable. We have low inertia systems, generally speaking, with wind. There's also deregulation, deregulated network and electricity markets, which was not the case in legacy networks. There's also increasing use of advanced protection and control methods. And all this requires more precise control of power. And typically this is done through the use of power electronic devices such as high voltage DC transmission systems or flexible AC transmission systems. And there's also a grid intelligence layer on top of the power systems layer, and particularly when you have smart grids. So it's quite a different kind of network. To cite a few examples of the modern power system, here's the example of a high voltage DC transmission system such as is used in the Nelson River transmission system in Manitoba, where I come from, where you have gigawatt power level power, or 6,000 megawatts in our case roughly, being transmitted from one end to the other end over a 900-kilometer transmission line, or a set of 900-kilometer transmission lines, and through power electronic equipment such as the ones that you see on the right hand side here. Just to show how prolific HVDC transmission has become, this slide shows the HVDC transmission systems in North America. You have long-distance transmission systems such as the Nelson River system I just talked about, or the Quebec-New England system over here, or the ones in the Pacific Intertie. You also have a lot of back-to-back HVDC systems that are necessary for connecting the Western and Eastern systems, or the Eastern and Texas systems together through asynchronous ties, because the DC offers asynchronous operation. One of the things you can see in this picture is that, particularly on the east side, a lot of these systems terminate in the same AC network. This situation is called multi-in-feed HVDC systems, and so it's no longer enough just to model the DC network in isolation connected to AC networks on both sides. You also have to model other DC networks or DC transmission systems in the vicinity as a multi-in-feed DC transmission structure. And also you're getting this multi-terminal HVDC system, such as the Quebec-New England system, which has multiple HVDC terminals. So this is creating a lot of interesting modeling requirements. There is a lot of talk about connecting continents together using HVDC. And here's a map where you have solar energy in North Africa provided with DC connections into Europe, and again offshore wind generation in the North Sea and other places, and all connected into a big DC grid for the entire. This is a multi-continent DC grid. So such grids are in planning, and hopefully in the future we might even see them. And of course we shouldn't forget smart grids and microgrids, which are essentially grids that are very accurately controlled by a computing layer on top, so that you can maximize their utility and also maximize the use of renewable energy. And this combines communication, computers, and power in the same grid. And this also puts on some special requirements for modeling. I'll say now a few words about the challenges to simulation. And traditional far frequency modeling techniques such as transient stability analysis programs, which model things in a phasor domain, are generally not possible when you start using power electronic converters, which require detailed electromagnetic transient type modeling. And so they require very small time step and very detailed models. And the interconnected nature of the grid requires the inclusion of large geographic areas. That's always not possible in full detail in all areas because of the limited capability of computing equipment, although that capability is growing as time goes by. And so some of the solutions that are proposed are hybrid simulations using interface simulation environments, model reduction of large network areas to simpler representations, and then of course the use of parallel processing. This slide just shows the kind of studies that we might want to do with simulation programs, ranging from very fast transients such as lightning and impulse and switching transients, to very slow events like long duration variations, load variations, and so on, and then a whole range of things in between. Now, The transient stability simulators that were used in the past generally model things into the 1 cycle or range and above in terms of time. And for HVDC infects and other things like that, we need electromagnetic transient simulation, which is the most detailed type of simulation. And it can model basically the whole range of simulation studies that we want to do. It can model the switching more accurately. Of course, it can take care of the slower frequencies as well. So this is kind of the range. We'll be concentrating more on the EMT simulation and also the interaction or hybrid simulation, including transient stability and EMT together. Several methods are now being proposed for offline simulation of power systems. I'll talk about real-time simulation, which is different from offline simulation, a little later. And they typically exploit the multiple computing cores that you have on modern central processing units in a computer. There's also a lot of use of graphical programming units. Graphical programming units typically are used by gamers and other people who need highly efficient graphing mechanisms, and these are typically quite inexpensive compared to CPUs, and if you can array them together, you can use them for computing. Similarly, for field programmable gate arrays, can give you additional parallelism. And of course, then you can use more advanced methods for partitioning the problem into solvable chunks using graph theory. You can also look at additional, combined with graph theory, look at additional factorization algorithms to invert the blocks of matrices that you get in the simulation. And then you can also, with this, you can achieve fully automated parallelization through matrix level partitioning. And this is different from earlier approaches where we typically partition the network using transmission lines, utilizing the fact that information on one side of the transmission line doesn't reach the other side of the transmission line immediately. So you can actually model both sides on separate processors without the need for communication at this present time step. You can pass the signals later on in later time steps. Here's an example for here on the top you see the admittance matrix of a large network, and it's when it's processed using graph theory approaches, you get the matrix structure shown below. And the advantage of the matrix structure below is that there are well-defined square matrices, such as in these 3 blocks here, with the off-diagonal elements sort of how much communication is required between the two. And so you minimize the off-diagonal elements and get big structural blocks like this. And if you reformulate the problem in this way, its computing requirement can be significantly reduced because now you can do many things in parallel. Here's an example of the simulation of a 7,000 bus system on multiple cores. We used a 64-core computer here. Partitioning was done using graph theoretical methods, and you can see as you use more and more cores, you get considerable speed up, almost linear, until a factor of about 42. Beyond that, there is no more further parallelism available, and using more cores doesn't give you any advantage. In fact, it gives you diminishing returns. Now let's talk a little bit about hybrid simulations. It is often impractical to model the entire system in detail on either an EMT simulator or a single simulator. And so we could divide the larger system into several subsystems which are simulated using different simulation tools. For example, where detail is important, the components can be represented in full electromagnetic transient detail. This would include components such as HVDC converters, static var compensators, or StatComps, or some other equipment like that. And other subsystem elements can be reduced order models, such as can be implemented easily on transient stability models. Here is an example of a simulation of a large AC-DC combined system. You have an AC network with multiple DC infeeds on the right-hand side here. And then you have 2 HVDC links that are terminating in this area on buses number 3 and 8. These can be modeled on an EMT program. The rest of the network can be modeled on a transient stability analysis program because it's mostly AC networks. Now, one of the things that the transient stability program does not do is it does not represent higher frequencies. So what can be done is there can be a certain combination of the two approaches, a hybrid approach used in the middle, whereas you put in the EMT program a frequency dependent network equivalent that represents the high frequency behavior of the external system, which is not modeled in the TSA program. And that is inserted into the EMT program here. In this particular case, we had modeled this on a real-time simulator, but it doesn't matter whether it's a real-time or offline simulator. The same technique can be used. You have transient stability analysis on this side. You've got the full EMT simulation on this side. You've got the interface here, which really is just a current source, which transfers the TSA information to the DC link. But in addition to that, you also have these frequency-dependent network equivalents, which you put on that bus bar, and they represent the high-frequency behavior of the AC network so that you get accurate simulations even at high frequencies. So then this is the essential approach I described on the previous page, where the TSA and PSCAD models the real-time EMT models are running in parallel with each other and exchanging information. And you can see that if you look at the time comparison of this, it is the black line over here at the bottom is the time required for the hybrid simulation. And if you had used EMT alone, you would have got the green line here. So you can see that there is a considerable improvement in time. We have only a few seconds of simulation time for the hybrid approach, and it doesn't really increase that much as the number of buses grow, because most of the time is in the EMT simulation, and the EMT is only simulating the two hybrid links. Whereas if you model the whole thing in EMT, then of course the computation time would increase significantly. Yes, I had talked a little bit about in the previous couple of slides about frequency dependent network equivalents. They represent the high frequency behavior of the transient stability side, larger AC network, and place it on the EMT side of the simulation. And obtaining the FDNE is not a trivial task, and there are many methods to do this. One of them is described in this paper by Dr. Hu and our group. They were from Tsinghua University, and the reference is given down here. Even after you separate the problem into TSA and EMT, you still have a further saving that you might be able to squeeze out of this by taking the machines that are swinging coherently with each other and representing them by an equivalent. So in this case, we have an internal system which is modeled on the EMT program, and then we have this external system which has many generators and many buses. But what we can do is, because some of these swing together in coherence, we can then reduce them into only a few machines that are connected there, and therefore you can reduce the size of the problem considerably. And there's a reference given here for that. Yeah, here's an example of a 2300 bus Southern Alberta network. This is an actual simulation that was done. And the system was reduced using the methods I just talked about. That means that part of it was represented in TSA, including the coherency generation, and then part of it on the EMT program. And the whole model could be squeezed on two real-time digital simulator racks. In this case, a digital real-time simulator was used, but could be done on an offline simulator as well. And the point is that with a very limited amount of resources, you could model a very large system, in this case, even in real time. Now let's look at real-time simulation, where we model the EMTB algorithm on multiple CPUs, but running at a time step which is in synchronism with a real-world clock. And that way we can actually connect real equipment, control equipment, or even power equipment to the digital. Well, here's a case where of a real-time simulator being used to actually test a physical device, which is a photovoltaic inverter. It's an actual inverter connected into a simulation. And the interface, of course, is high power amplifiers, which take the digital signals and transfer them to actual physical signals and feed the PV inverter. So you can do testings of this sort. This slide was given to me by Dr. Misha Steurer, who's at the Center for Advanced Power Systems. They too use the RTDS simulator, which is manufactured in Winnipeg and originally designed by some of my graduate students. Here are some of the other things that are being done these days. This shows the simulation of a microgrid, which has a electrical distribution network for a small area, And on top of that is a cyber physical control layer consisting of computers and the communication between them. And the computers and communication is simulated on a simulator called UpNet. The electrical network is simulated on the RTDS EMT type simulator, and the two communicate with each other with some suitable interface. And then on the UpNet simulator, you can either do physical faults on the communication system, or you can also do things like denial of service attacks, hacker attacks, and so on the network. So you can see how the power system would behave if the cyber physical network was misbehaving. My last example is a power hardware in loop simulation of wind generators. So for example, if you have a wind generator, which is actually a physical device, an actual one, then you can have an EMT model in a real-time simulator of a large power system, and the signals coming from that you can pass through an amplifier and apply voltages to the real wind generator, so the wind generator would think it's connected into the real network. And then you also have a model of the wind turbine and the wind system, which you could simulate on another computer and then drive an electric motor, which is the prime mover for the wind generator. And that way you could actually study the transients on the wind generator as though it were connected to the real network. Here is a setup of the facility at the of the E.ONS facility in Aachen, Germany, at the University of Aachen, where they have so here is an actual wind generator under test. There is a prime mover driving it. The prime mover is the mechanical side of it is simulated using this computer over here. The electrical side is connected to the RTDS, which is in a separate room, and that models a network, and it can be as large as you want, and through an amplifier. And the amplifier, of course, these can be multi-megawatt amplifiers because they have to be similar ratings to the wind generator itself. And so you can study what would happen in the wind generator if it were really connected to the network, and you can put it through its paces. And such facilities are springing up all over the world. There's one, of course, in Germany. Then in the United States, they have a facility which they claim they will be soon moving towards testing of up to 15 megawatt wind generators as though they are connected to the real network. We saw in the previous slide an example of some rather large equipment connected to physical simulators. But in order to do this properly, you also have to build accurate and stable interface equipment, such as these amplifiers and so on, so that you don't get errors arising from the interfacing technique. So here in our laboratory, we had an example of a STATCOM, which is a static synchronous compensator, which is a physical device connected into a simulated model of a power system. And we wanted a stable and accurate simulation of this. So what was done here is that we had to put some interface filtering, and that could be designed with certain algorithms that are described in the paper that is mentioned here. And then we also had to do some signal conditioning when we are transferring signals over, and in order to get accurate and stable simulations. I'll just conclude my presentation with a few remarks. The hybrid structure of the modern grid, which has a mix of power converters and new energy sources and legacy generation, has put a challenge on simulation tools. And so the simulation tools for such networks must be carefully selected due to the different computational requirements of each subsystem. New computer platforms harnessing parallelism are proving to be useful. Hybrid modeling of our TSA and EMT models are interfaced allows modeling of very large networks. Interfaced real-time simulators allow power hardware and loop testing of actual power equipment, including the cyber physical controlling layer. And so we can conclude by saying that the future of simulation is exciting. I'll just end by giving some acknowledgements to some of my graduate students and other colleagues that from our university and other institutions that have given me input that I used in this presentation, and they're all listed here. I won't read them out one by one. And I've also given a bunch of references at the end. So thank you very much for patiently listening. If there are any questions, I'd be happy to answer them.
Thank you very much, Annie, for that wonderful presentation on modern power grid modeling. There's certainly a lot of challenges to be seen there with the integration of HVDC and power electronic converters into the AC systems. It was good to see how much HVDC is expanded throughout the world. but you've definitely highlighted some challenges in the modeling, but also providing some methods of tackling those challenges through hybrid simulation and reducing the model into easier bits, and also providing examples of both offline simulation and real-time simulation with some great hardware in the loop examples, such as StatComs and wind turbines. So thank you very, very much for that presentation. Now we're going to move on to our next presentation, which is around Workstream 2, and this is by Professor Freddie Bludgeberg from Aalborg University. So Freddie was with the ABB, Scandinavia, Randers in Denmark from 1987 to 1988. From 88 to 92, he got his PhD degree in electrical engineering at Aalborg University in 95. He became an assistant professor in 92, associate professor in 96, and full professor of power electronics and drives in 1998. From 2017, he became volume investigator, his honoris causa at the University Polytechnia Trimorsa. I'm not very good at these European names, sorry. In Estonia, he has received 33 IEEE prize paper awards, the IEEE PELS Distinguished Service Award in 2009, the EPE PEMC Council Award in 2010, the IEEE William E. Newell Power Electronics Award in 2014, the William Kahn Rasmussen Research Award in 2014, the Global Energy Prize on Power Electronics from 2006 to 2012. He's been a distinguished lecturer for the IEEE Power Electronics Society from 2005 to 2007, and for IEEE Industry Application Society from 2010 to 11, as well as from 2017 to 2018. In 2019 and 20, he served as president of the IEEE Power Electronics Society. He has been vice president of the Danish Academy of Technical Sciences. He's nominated in 2014 to 20 by Thomson Reuters to be between the most 250 cited researchers in engineering in the world. So it's a great honor to have him present for us now.
Hello, everybody. Welcome to this presentation about reliability analysis of fault-tolerant power converter system. Thank you very much for the possibility to be here and discuss this topic. So what I will do in my presentation here, first I'll do an introduction. Next, I will discuss topologies for three-phase fault-tolerant inverters, which is the topic here, and then also come up with how to analyze such kinds of systems, applying reliability analysis and especially Markov chain, and then at the end some conclusion of my presentation. But first, a few words where I'm sitting today. I would have loved to be in New Zealand. It's a fantastic country and attend this conference, but that's not possible in these times. So I'm sitting up here in Denmark and do the presentation. We have 12 hours time difference as such. And the university I'm hired at, this is Aalborg University, where you have the Danish map here with Copenhagen situated here, and then Aalborg is located up here. Aalborg is a city with around 200,000 people, and the university has 22,000 students. The university is famous for the problem-based learning. That means all our students, they work in teams and working with problems. And we have even something we call a PBL, Aalborg model, which is quite famous around the world. Maybe not as famous as Hans Christian Andersen, which I think some of you might know through your history. Aalborg University is also famous for the engineering program. It's a rather strong program, and some of the ranking systems are ranking Aalborg University quite high. For example, the US News ranking, which is a lot based on research outcome. And you have here a few photos from our campus area. It's a nice campus area. We are located both in the downtown and a little bit outside city. And you can see we have a lot of water and also nice weather. But I can tell you for the moment, the weather is quite cold, and we have been hit by snow in the last 7 days. But it seems to be melting now. But the topic here, and in general also what is gathering us together, this is about the power system, which in my opinion is really undergoing a big transition from being, let's say, conventionally based on a few generators. Then we have transmission, distribution, and use of electrical power to become a much more diverse system with a number of different generators, PV and wind, but also a lot of controllability at the load side through power electronics. And in the recent years, there is no doubt that the transportation is undergoing a big change, and there we would have storage also in our system to be an active part. And for example, a plug-in hybrid car or full electrical vehicles, they are also going to play a role. But what is really interesting to also see is that the blocks here, the power electronic units, they are sitting everywhere, and we have to master them in terms of being reliable and operate as we expect them to do. And on the other hand, also be sure that they are not too expensive. So there is an optimization in that respect. So in order to have a picture about this, the reliability analysis of the product we are making in power electronic products we are making is very important. And for the moment, a lot of activities are going on in order better to understand what's going on. And in general, we can say most of the reliability analysis now are becoming, let's say, very dependent on the real physics behind the components. And then in a systematic way, we become able to analyze it and being able to predict how many failures a certain product will see over lifetime if they see a specific loading conditions. So what is really going on in terms of reliability analysis is that first we look at the failures which might happen. Then we do a stress analysis of the system, as what is the system, the components and the converter is belonging to. Then we do strength modeling, how strong is our design, and based on those two elements, we also we can say something about its reliability. And in this overall mapping, many different calculations are important, and we get indirect metrics like how the temperature is, how the voltage and current stress are on the system, as well as we also get specific metrics out of it, like failure probability or lifetime for a certain population, and you see some photos here. But what is really important in this analysis is to understand the system we are having, which components are the most critical, and then we try to analyze them. So if we look at it and we want to make the system more reliable, one of the approaches is to make fault-tolerant operation. And if we make fault-tolerant operation, then there is a higher probability that the system we are having, this can be have a longer reliability and and also stability. So if we look at it and analyzing systems, we can operate at different levels. We can operate at converter level, and for example, illustrated here with a PV inverter where one component is failing, and what happens in such case. And why does it fail? And in that case, of course, we have to find solutions to ensure that it can still operate if one is failing. But then we also have the possibility at system level to have kind of redundancy, illustrated here with a PV power plant with multiple string inverters, and then if one fails, then the rest can still operate. So this is kind of redundancy in the system. So also at system level, we can try to make it very robust. So when we look at such kind of converter, well, we have to look at, okay, what can happen? So which topology do we have? How can we reconfigure the system so it can still operate? And how, after it's reconfigured, how do we then do control? And in order to do this, of course, and be sure it's still operating afterwards, we also need methods to do fault detection and isolation. And this is, of course, interesting because if we can do it, the reliability will be higher, and we can analyze different situations. We can analyze a single event failure. We can analyze a way out failure. And then, of course, when we do something, we have to look at it as a system performance perspective, as what is the benefit seen from a cost perspective. Does it make sense to introduce this, or should we put in another maintenance strategy? And then before we expect the failure to happen, then we do a change. So there are also some preliminary studies we need to do in order to make a decision what is the best solution in order to achieve fault tolerance. And fault tolerance in voltage source inverters, this has been there for many years, and we can get inspiration, especially from the motor drives, where the fault tolerance especially came in the airplane industry and so on, because it was 100% sure that they wanted to have a very safe system. So what we can look at is, of course, topology, system reconfiguration, and then post-fault control. So we still are able to operate the motor. And as told before, it is all about cost and performance. And what are the solutions? There are switch redundant topologies, there are double switch redundant topologies, there are phase redundant topologies, and then we can also play with different other topologies. So if we look at the switch redundant topology, then what can happen here fundamentally are two things. Also, one is that the device is open circuit or it's short circuit. And what the philosophy here is that we introduce the possibility of each phase to be connected to the midpoint of the capacitor. And in that case, of course, what we need to be sure is that we have access to neutral, and this is okay. And then in case the fault is there, either open or short circuit, then we can connect this point to this point. And then we are operating the system like what we in the old times called a B4 topology. The disadvantage with this one here is that the output voltage will be reduced by 50%, and the current will be higher in case that we need to have the same power. Plus also the caps here will be loaded extra. But anyway, it gives you fault tolerance, no doubt about this. Then we have what we call a double switch redundant topology, where we have the three phases. We have then an extra leg in order to be able to operate like the one which is faulting, and then dependent on its open circuit, short circuit, then we are using a fuse here to be able to ensure that we have an isolation of the specific phase which have a fault. But the control is the same like you saw before, and we have access to the neutral in order to be sure that we can still operate the system. And here you can see a more full implementation of such kind of configuration. And then we can also do what we call a phase redundant topology, like illustrated here, where we do not have contact to the midpoint of the capacitor, but we just have a leg here. And what we do is that we can isolate the fault phase, and then we can connect the fault phase to the extra leg here. And then, seen from a control perspective, we fundamentally have the same topology like in case that it was before. And of course, in this case, what you can see here is that, yeah, we need extra 2 diodes and 2 switches in order to be able to achieve what is necessary. As well, you can see here that fuses are included to take into account the case that we have a short circuit and then become isolated in that case. So we do not have a short circuit of the DC link. And of course, everything is about money. So we have at least three solutions in order to achieve fault tolerance, and there are pros and cons. 2 of them need neutral connection, 1 do not, and one of them is not using extra power switches, but then the voltage we can achieve is less. So it's always pro and con. So, but fundamentally, if we look at the system here, then the phase redundant topology here is the most attractive, as we do not see any limitation on realizing it. So as said before, what we can do with this one here is we can isolate the faulty phase, we can connect it to this extra leg we have here, and then we can fundamentally operate like we did before, which is an advantage. Also, the DC bus is not connected to the neutral, so that means we do not have the fundamental current flowing in the capacitor. They don't have to be so high. And yeah, but the challenge is, of course, a little bit more components compared with before. So how to assess this, and in order to say something about the reliability, and what we normally do is we are applying a macro chain where we are saying whether the component is up, as is working, or the component is not working, is down. And this is a little bit illustrated here, where we are using state diagrams in order to say whether the function is like we want to be. When we are applying macro chain in order to calculate the reliability of a system, we all fundamentally assume that there is a constant failure rate of the system, and that can maybe not be the case, because after the fault we still have other components which have a kind of history, and that is not the case for the macro chain, because it's really memoryless. So we start from the beginning again. And what we can do is we can put up this equation here to describe the functionality of the system. So we can also see that when we have the topology, we do not only have one, but we have n components, right? And they can either be up or down, depending on whether they are operational or not operational. And then if we have n of them, and if we are assuming that if just one fail, then the system is failing, then we can, in the Markov model, model it like this one here, and also then make the equation here in terms of how to describe the reliability of the whole system. So in reliability engineering, we also, as one is to apply Markov model, another one is to use a reliability function, and just to illustrate that here, that fundamentally we get some of the same things in the case that the lifetime is constant. We have a constant failure rate. So in the reliability block diagram, the way we will do this is that we have this for one, and then there's in series, and if one is failed, the whole system is failing. And if we look at the system reliability, depending on how many components we are having, we can see that this is decreasing as we get more and more, as we have more and more components in our circuit. So if we are then introducing fault tolerance, then we can say, and this could be achieved, for example, with a circuit like this, but not 100% like what you saw before, but just a fundamental idea. Then we can say, okay, we have two components in parallel, and what can happen is that both are okay, right? Then everything is okay. One is failing. This could be this one here, but then the circuit still is okay. And then they both are failing, and then it's not okay anymore, and then it's in the fail state. So this is a little bit illustrated here in the state space formulation of the system, that in two of the cases we are still okay, and in one of them we are not okay. And seen from a reliability perspective, with fault tolerance, without fault tolerance, we have a description like this. And if we then have fault tolerance in the system, then you can see that the reliability of the system is increasing. So if we are applying this way of modeling and take an example of a little bit more complicated system, which is illustrated here, which have really a fault tolerance in the system, where you have a back-to-back converter, you have a kind of breaking a chopper here, or charge or buck boost converter in order to do it. And then we have a redundant leg, which is able to, let's say, have fault tolerance on both sides of this one here. Then we have the case that we have in total 14 IGBTs, and if one fails, then we are still up. And then if the triac fails, then we are really moving into the state where it's not working. And if we look at this, and we have a failure rate of the IGBT and triac like this, then we have a system reliability with which, if we just have n legs, and then in the case that, now if we have a three-phase system, then we have this reliability function, and if we then put in the fault tolerance, then we get a much more improved reliability given by this curve here. So what you have seen here, this is a way to increase the reliability of voltage source inverters, where it's taken from the motor drives. We can apply phase redundancy in different ways, but of course we should have in mind it might cost in different ways, either the capacitor or the number of switches, and we have Markov chain to describe that when we have a constant failure rate. But yeah, the next steps are, of course, being able to take into account that we do not have a constant failure rate in case that we do the analysis, and work need to be done in order then to assess the system we have achieved. Yeah, so this was just a touch base on how to do a reliability assessment of power electronic system, and in fault tolerant circuits. And with that, I hope you got inspired for future research, and I'll be happy to answer questions you might have. So thank you very much for your interest in this presentation.
Thank you very much, Freddie. That was a really interesting talk. Thanks for introducing us to Aalborg University and giving us some key aspects of the reliability analysis, such as failure identification and stress analysis and strength modeling, which leads to the reliability mapping, and how giving some examples on voltage source inverters topologies that can be used to improve the reliability, such as switch redundant topologies or the phase redundant topology, and then showing us an application where we can use the Markov chains for assessing the improvement in that reliability. So thanks very much for that talk. Moving right along, because I noticed we're about 10 minutes behind schedule. We have our next talk by Professor Ioannis Lestas from University of Cambridge. He's an associate professor at the Department of Engineering in Cambridge, and he received his BA Starfirst and MEng distinction degrees in electrical engineering and information sciences, and the PhD in control engineering from the University of Cambridge Trinity College. His doctoral work was performed as a Gates Scholar, and he has been a Junior Research Fellow of Clare College, Cambridge, and has also been awarded a 5-year Royal Academy of Engineering Research Fellowship. He is the recipient of a 5-year ERC Starting Grant. He is currently serving as Associate Editor for the IEEE Transactions on Smart Grids and the IEEE Transactions on Control of Network Systems. His research interests are in the area of control of power networks and smart grids. So thanks for your talk.
Hello everyone, my name is Ioannis Lestas. I'm with the Department of Engineering at the University of Cambridge, and we're really glad to be one of the partners in the FAN project, a project that aims to address some very timely topics associated with current and future power grids. My specialization is in the area of control, with a focus on power system dynamics and decentralized control. In this presentation, I will give an overview of recent work we have been doing associated with scalable control and power sharing in inverter-based grids. Now, first, an outline of the presentation. I will first give an introduction to the topic, and I will then describe various methodologies that can be used for scalable control design in inverter-based grids. These techniques will be based on so-called age infinity and passivity type of approaches for decentralized control design. I will then discuss how these techniques can also be extended to hybrid AC-DC networks, and in particular control design for interlinking converters in such networks. I will end with some conclusions and various open problems for future research. Now, first, a few introductory slides. There is an increasing amount of renewable generation, like solar and wind generation. There's therefore an increasing number of distributed sources which are DC interfaced via converters. This therefore leads to a decline in the prominence of synchronous generators, and such inverter interface generation leads to a so-called reduced inertia, which has important implications in the dynamic behavior of a power grid and raises various significant control challenges. This slide describes the typical timescale separation encountered in conventional grids. Tertiary control is at the slowest timescale, typically of the order of hours, and this is basically an optimization problem that adjusts the set points of the network based on operational constraints and also forecasting for demand. Secondary control is at a time scale of minutes, and this recovers the frequency and voltage to nominal values. Primary control is at a time scale of seconds, and this is associated with frequency and voltage control. And the inertial response is at a time scale of milliseconds, and this is associated with the physical response of synchronous generators. Now, in an inverter-based grid, this inertia of the generators is not present, and therefore this response at the very fast time scale, this time scale of milliseconds, is implemented by the control policies of the inverters. And this is in general a highly non-trivial control problem due to the fast time scales involved and also the potential interaction between the different converters. Now, in an inverter-based grid, inverters need to have also a grid forming role, meaning that they need to control the voltage and current and also synchronize with other inverters. And this is a non-trivial problem, as it was mentioned before, due to the fast time scales involved, and also the tight ratings of the converters, and the fact that these control policies need to be decentralized, due to the fact that the fast time scales involved imply that a centralized implementation would not be practically feasible. Here we have a comparison of control implementation in conventional power systems and in converter-based microgrids. So in conventional power systems, synchronous machines provide frequency and voltage regulation, and converters use phase lock loops to synchronize to the grid. On the other hand, in a converter-based grid, frequency and voltage regulation is provided by the converters. And the challenge we want to address here is the following. We want to design decentralized control policies for converters such that we have stability of the network in a general network topology, and also good power sharing properties, so appropriate power allocation within the network. For our analysis, we use the following representation of the microgrid dynamics. So we see a microgrid as an interconnection of bus dynamics with the line dynamics. And it should be noted that the line dynamics are quite important here due to these millisecond time scales involved. So the bus dynamics have as input the current injections and as output the voltage. And similarly, the line dynamics have as input the voltage and as output the current injection. Now we're considering here an AC grid, therefore a DQ transformation needs to be applied. However, the reference frame that is used in this transformation needs careful consideration. So if we use a local reference frame at each bus, then this would simplify the bus dynamics, but it would complicate the line dynamics. And if, on the other hand, we use a common reference frame, then this would simplify the line dynamics, but this would complicate the bus dynamics. But on the other hand, an important property we get when we use a common reference frame is the fact that the line dynamics preserve their natural passivity properties under this transformation. And this is a very important property when we want to do decentralized control, as we'll discuss in the next slide. Now, since the line dynamics satisfy this passivity property on a common reference frame, a decentralized condition for stability is to design our controllers such that the bus dynamics are also passive in this common reference frame. And it should be noted that this is a decentralized condition, and it holds for a general network topology because the line dynamics have this passivity property in a general network. However, satisfying this passivity condition is in general a non-trivial problem. For example, this is not satisfied when conventional droop control policies are used in grid-forming inverters. So we tried various parameters and we have not been able to satisfy this passivity property, which implies that some more advanced inverter control designs are needed in order to have these stability guarantees by means of decentralized control policies. It should be noted, however, that this passivity condition is easily verifiable. So for a linear system with transfer function g of s, it can be checked from the eigenvalues of g of j omega plus g star of j omega. Or it can be checked in the time domain by means of a linear matrix inequality involving the A, B, C, D matrices in the state space representation of the system. So this is basically a convex feasibility problem. So in the last couple of years, we have been trying to come up with a control design for grid forming inverters so as to satisfy this decentralized stability condition, which would give stability guarantees for our network and also allow a plug and play capability. And it turns out that this can be satisfied by means of a state feedback controller used together with a virtual impedance. And this virtual impedance improves also the power sharing properties of the network, particularly at faster timescales. We also went one step further and incorporated additional conditions so as to improve the dynamic performance of the network. In particular, we incorporated so-called age infinity type of conditions on appropriately formulated closed-loop transfer functions. And an important property here is that the control synthesis problem, where we aim to satisfy this passivity property and these age infinity conditions, is a convex optimization problem that can be formulated by means of linear matrix inequalities. It should also be noted that our controller here is dynamic, rather than just being a static state feedback policy. Here are some simulations that illustrate the behavior of such a scheme. So we have this configuration with two converters and various load buses. And we see here the voltage response when there are step changes in the load. And we see that this mixed age infinity passivity controller performs very well. So the system is stable with a very fast response with hardly any overshoot. However, a very important feature we get from such a design is very good scalability properties and plug and play operation. So in this case, an additional converter was added to the system, and we checked again the step response. And we see here that a conventional frequency droop scheme performs very poorly, whereas this mixed age infinity passivity controller still maintains a very good behavior, very fast response with hardly any oscillations. These ideas also extend to hybrid AC-DC networks, and in particular the problem of control design for the interlinking converters. Now, passivity approaches have been used in the literature when DC grids or AC grids have been individually studied. In particular, they have been extensively used in DC grids due to the fact that, again, the lines have natural passivity properties. And actually here, the analysis is even simpler because we do not need to carry out a DQ transform. So again, a sufficient decentralized stability condition is to ensure that the bus dynamics from current to voltages are passive. For the case of AC grids, we use in our analysis for simplicity different coordinates. In particular, we use the real and reactive power and frequency and voltage as inputs and outputs respectively. Now, when we consider the aggregate AC-DC network, a convenient block diagram representation is the following. So we have here the line dynamics associated with the AC network. These are the line dynamics associated with the DC network. And this block here is passive due to the passivity properties of the lines. Therefore, if the AC buses are designed to be passive and the DC buses are also designed to be passive, a sufficient decentralized condition for stability is for the interleaking converter to be designed such that this is passive with respect to the inputs and output specified here. So this is our design objective in our control policy, so as to have good scalability properties in our network. However, again, satisfying this condition is a highly non-trivial problem. And it turns out there is here a fundamental trade-off between good scalability properties and power sharing. And we illustrate this by considering two control schemes that have been considered for interlinking converters. So in the case of a dual drup, the passivity property can be satisfied. However, such a scheme is known to have very poor power sharing properties. On the other hand, matching control has good power sharing properties, but on the other hand, we have not been able to satisfy this passivity property with this scheme. So our proposed solution here is somewhere in between. We propose an integral dual drup scheme that will give good power sharing properties, and this is implemented with a leaky integrator and also a phase lead compensator, so as to ensure that the passivity property is satisfied. And here we illustrate some simulations when this scheme was implemented in this configuration. We see from the voltage response that the system is indeed stable. Here we compare the power sharing properties of this proposed scheme and a dual drup scheme. We see indeed that the dual drup scheme has very poor power sharing characteristics, and these are significantly improved with this integral dual drup scheme. So these are the topics I wanted to cover with this presentation. I will end with some conclusions and some open problems that can be used as a basis for further research. So I have discussed how scalable control designs can be achieved in inverter-based grids by means of appropriate input-output conditions on locally defined subsystems. And these have been applied in AC microgrids and also in hybrid AC-DC networks, and in particular the problem of control design in interlinking converters. Now some open problems and directions for future work. It would be good to try and go beyond passivity so as to reduce the conservatism in these decentralized stability conditions. And this is actually part of our ongoing work, and we try to achieve this using some more advanced tools in control theory, in particular so-called integral quadratic constraints. It would also be nice to get scalable control designs with drup-based schemes, as these have a simpler communication structure, since they do not require an additional communication layer to achieve synchronization. We're also trying to get guarantees, stability guarantees, with more advanced inverter models, in particular in the case of hybrid AC-DC networks. And it would also be nice to get scalable control designs that take also harmonics into account, which is a very important issue in power electronics based grids. Here are some references and also acknowledgements to our funding providers. So the first two references are the two main references associated with the material I covered in this presentation. So this brings us to the end of this talk. Thank you very much for attending, and I really look forward to many more interactions in the near future. Thank you very much.
Yes, thank you very much, Jonas, for your talk on control and power sharing on inverter-based grids. It was really interesting to see how inverters are leading to reduced inertia in the grid, and how it affects the primary control of the stability, and the challenges around decentralized control for stability and power sharing, and the importance of the reference frame and the passivity condition of the system. And it was great to see proposing some solutions with your state feedback controller, with the virtual inertia and the variable inertia and passivity controller added into that, and the benefits that had. So moving right along to our next presentation, this is related to WorkStream 4, and this is by Dr. Dan Martin from ETAL. in New Zealand. So Daniel Martin is a chartered professional engineer with 20 years experience in transformers and electrical systems. He's currently the convener of the SIGRAE New Zealand panel for transformers and reactors. He's also a senior member of the IEEE and a chartered member of Engineering New Zealand. His current role of innovation project engineer at ETEL Transformers. He leads and manages and completes innovation projects for new technologies. He has a PhD degree in electrical engineering from the University of Manchester and a Bachelor of Engineering degree of honours in electrical and electronic engineering from the University of Brighton, UK. Before joining ETEL Transformers, he was lecturer at the University of Queensland, with his research interests being on transformer technology. And prior to that, he was director of the Transformer Research Centre at Monash University. So great to hear your talk, Dan.
Good morning. Welcome to my presentation. So thanks for having me. It's great to see such engagement in this IEEE presentation. I think that's fantastic, even given with all the issues we're having with COVID. So to give you an idea, so my background is that I've got about 20 years of experience in power transformer insulation. So I did my PhD at the University of Manchester, and then I moved to Australia, working at Monash and University of Queensland. And now I'm the innovation transformer engineer at a manufacturer in New Zealand. So ETEL is supporting the University of Canterbury on their FAN project. So this is how we've ended up contributing to this, which I thank everybody so much. So to give you an idea of what this presentation was on, this is some work I did about 2 years ago in Queensland with Professor Ferouz Zair there. So Ferouz's research interest is power electronics. And in Queensland, we were seeing a lot of converters and inverters coming on the system. So there's a lot of solar going on there. There's also looking at wind, looking at electric cars, and everything. So we were starting to just think to ourselves, with all these power electronics, what is it actually going to be doing to the existing transformers and electrical infrastructure, which was more meant for linear loads. So we got together and we started looking at this, and we ended up producing a paper, which is the title is given below. So that was published last year. And I'd like to recognize my authors there as well. This is a joint effort that we were all involved in. Now, in terms of why I'm giving it at this conference, I thought it was very apt. If we're now talking about the DC grid and future networks, what I can really see is large-scale infrastructure. Probably a utility can expect anywhere between 50 and 100 years out of it. So what this means is, even with ideas about moving to DC, we're still going to get this blended network until maybe even up to the 21st century. So you can really start to see here the importance that if we're moving to the DC world, then how do we keep this combination of AC and DC running together? And one of the things we can see here, or one thing we have to keep an eye on, is that if any power quality or harmonics or anything like that come out from the DC system and starts to enter the AC, enter the transformers on it, then what will it actually do with them? So in terms of why this is important, one point with new customer technology is that it can rapidly increase. So it's not like a linear rise. It's usually once the cost of technology comes down, suddenly you get the tipping point and it takes off. So in terms of a DC grid, it's the same there. Some points might be quite expensive or not really quite maybe usable right now just because the cost is so high. But once there's that demand, things can take off very rapidly, and definitely within the several decades operating life expected of a transformer. We're also looking at here is that, well, we have other things which are DC based, things like EV charging, that's going that way. So we can start to see more power electronics coming on the system. We're also seeing more rooftop PV and home generation. One of the big problems we have, well, the utilities have, is how to make decisions today. So if they're looking at choosing or upgrading or replacing something right now, and if they're expecting to have it for 50 years, and they really do try and look out over the next 50-year period. So the simplest decisions might just be the MVA or KVA size, or are they looking at different voltage levels, those sorts of ideas. But if we're going to now throw into the mix a possibility in the future that we may just get rid of the AC and have DC, then it just provides them something else to think about. So other points we've seen happening is, one thing is the inverters. So they have a particular switching frequency, and we have, and I'll show this in this presentation, noted harmonics coming out the switching frequency of devices. And what we can start to sort of see what is actually happening in manufacturing right now is generally switching frequencies are increasing, and the manufacturers are doing that partly to increase their efficiency. Now, we started to get concerned about this in terms of, well, what's happening on the transformer, because the heat being dissipated within the transformer is highly inductive. It's actually related to the square of the frequency of the harmonic. So if we have fairly lowish order harmonics going into our transformer, and then we have higher harmonic frequencies, then we might actually find the heat dissipated is higher with the higher frequencies. It's not only just a function of the current. So we were looking at this, and then we thought, well, okay, if we can actually dissipate more heat within the transformer, so it's heating up, well, the life remaining of the transformer is a function of its temperature. So if you only need to go up maybe 6 degrees, and then you've halved the remaining life of the transformer. Now, usually in terms of rating, a transformer is designed and its rating to last quite a long time. So usually you get an inflection point where if you're looking at maybe 6 degrees increase, if it's at the lower ends or the lower loads, then it's probably not really going to do that much, because the life remaining will be fixed by maybe corrosion of the tank or other things happening around it. But if somebody is running the transformer at a very high load, and then we have another 6 degrees, say, of harmonics, then we've half the life remaining. So it can be significant. And all we would just say from this is that a lot of the distribution grid over here is not actually monitored. So an owner might not actually know what is going on it. And this is where we can see, if we're moving to a DC grid, then there'll probably be more monitoring involved. And that's just so that a utility is aware of what's happening, and then they can take the appropriate action. So as I mentioned before, the life remaining of a transformer is a function of the condition of its insulation paper. So this isn't to say that the transformer definitely fails on the condition of the paper. The transformer can fail on other aspects, something else going wrong with it, or even maybe corrosion of the tank can also be quite significant. However, the paper is the main core thing. When the paper has reached its end of life, then you can't really replace it. So we have here 2 graphs. So transformers can be either sealed or free breathing. Now, for smaller units, especially over here, most of them are actually, well, most of the new ones are pretty sealed. So the transformer paper, it's been kept away from the oxygen in the air. That helps prevent it from degrading. On the right hand side, we've got our free breathing units. A lot of transformers here may be mid MVA, maybe in the range of tens of MVA, those sorts of ranges. Chances are that they're not usually sealed, they're just free breathing, and then the air can actually get into the tank. The WCP there, that just refers to the water content of the paper. So this is just showing that as the transformer insulation becomes wet, its life expectancy falls. So in terms of applying these graphs, we've got a temperature along the x-axis. So normally, well, especially for sealed units, if you're looking at like a continuous temperature of anywhere, maybe depending on its water content, usually you're looking at between 70 and 90 degrees, then that means the life expectancy, depending on the water content, can be anywhere between 10 years and 100 years. So a utility may expect to get anything 30 years, 50 or even more, 70 years out of a transformer. And normally what they would do is that they would just try to keep the conditions within that zone. Now the temperature is a continuous long-term average unit. So within a transformer that we have, the load is and the ambient temperature is constantly varying. So what we would do is that we would look to convert a long-term, a continuous temperature measurement into a long-term average weighted temperature. On the right-hand side, we can start to see here that if the transformer is breathing, then the oxygen in the air can have a significant effect. So we can start to see there that we shouldn't be running the temperature of a free breathing unit at the same as a sealed unit if we wanted to get the same life out of it. So in terms of this, as I mentioned before, that roughly 6 degrees extra elevation in temperature will actually halve your life. So if we're taking a temperature transformer and it's fairly lowly, and at a low load, then an extra 6 degrees won't really do that much in terms of the life expectancy. However, if we're looking at running it at a high load with a lot of customers or industry connected on a transformer, then harmonics can become more significant. In terms of our transformer there, so what causes heating? So we've got one component, we've got the core heating by losses in the magnetic system. Now this is what we call the no-load losses, so it's independent of what is actually happening to the load current. In terms of a percentage, how much of our loss is due to core heating, it can be anywhere between 10% to 30%. So usually the smaller units have a higher core loss. It's just simply in proportion to the I²R losses in a smaller unit are obviously less. So when we start to look at the load loss heating, that can be anywhere between 70 and 90%, again, depending on the capacity of the transformer. And in that load loss, we have our I² losses and we have our eddy currents. We also have a certain component due to stray losses, such as in the tank wall. If there's any components which are magnetic, then they tend to produce higher stray losses than non-magnetic steel. Now, if we take current harmonics coming out from DC device, which are entering our system, so we're quite interested in these eddy currents, which can be anywhere up to half of the load loss. It does depend on the design again. And the relative impact of a current harmonic on these eddy currents is actually related to the square of the frequency. So this is where it's not just the actual load coming into it, but it's also the frequency of those currents. And if we start to look at a higher frequency harmonics due to something like an inverter, then we can ask, well, what is it actually doing to the transformer temperature? In terms of the IEC standards, the ones for transformers, they state the total harmonic distortion of current should be no greater than 5% at the rated transformer load for normal service conditions. So the transformer standards, they do give us an option that if there's higher harmonics are present, then a solution is to derate the transformer. Now, it's worth pointing out here, there's a bit of a difference where these standards for transformers, the 60076 series, are only considering the transformer. They do not consider the overall what else is happening on the network. So that's usually more in the 61000 series, where it discusses more about the power quality which is acceptable for the system itself, and the utilities may also have their own power quality requirements. But what we are concerned here is that in these transformer standards, if they're talking about the total harmonic distortion, then we can see there's a bit of a mismatch here between that and the effect of the harmonics, because the total harmonic distortion does not consider the frequency, whereas the transformer does. So what we looked at doing here, so we took a section of the network in Australia, and then we started to have a look at what is actually happening in terms of the harmonics. So here we got two, I suppose, medium-sized PV arrays. Obviously, this is not a very large solar farm. I mean, this is around about 1 megawatt size. So in some ways it's pretty substantial, but it's not the biggest which can be out there. And we have these two PV arrays, and they're connected through these inverters, and then we have our transformer, and then it's stepped up to the MV network, which is owned by the distributor. So we were starting to look here, first of all, the IEEE practice of what is doing it. Now, we think the IEEE is maybe just a bit ahead of the IEC standards, because there is one in the IEC for wind generation and transformers connected to turbines, which talks about derating. But it's not across the whole spectrum of transformers, whereas the IEEE practice is more well known. So we take this IEEE practice, and one of the things I do like about it is for an older transformer, such as on a public distribution network, it might be very hard for the utility to find anything about it, whereas this is easier to apply. So we're looking at here, we calculate our harmonic loading factor, and we multiply it with the winding eddy current, and then we can calculate the display losses. And then when we know these total losses, then we can calculate what is the temperature rise within the transformer. And then we can start to look at the relative rate of vapor aging. Now, what we found, which was actually notable to us, was when we were looking at the harmonic order there, that we can see these two peaks. So these are both around so one at the 58th and 62nd harmonic. But we found, surprisingly, so that was around the switching frequency of the inverters. But it wasn't a sort of a slow roll-off of harmonics from maybe a few lower order ones slowly disappearing down. It was more like they were becoming maybe lower as we were moving along, and suddenly, all of a sudden, you've got these peaks. So then we were thinking, well, in terms of the transformer, what is it doing? And we found that they together had a combined effect of 33% extra heating. So we thought that was actually quite surprising. Now, in terms of the transformer itself, there wasn't, I guess, really that much happening in it. Maybe there was 2% increase of load. And that then we calculated a 2-degree increase in hotspot temperature. Now, 2 degrees sounds probably not that much, but that does mean it's actually ending up around 21% faster consumption of paper during daylight hours. So in terms of what does it mean for the transformer, if something is being run at quite a high load, and then we add 21% faster during daylight hours, then that can be pretty significant. Whereas if it was maybe not really that loaded, then it might not really do much. In terms of our suggestions and what do we think should be done about this, so we can really see that there's maybe more monitoring and calculation methods of harmonics to determine what is actually happening at the transformer. Now, some transformers might have monitoring on them. A lot of them here, the smaller ones, don't. So we can see a role in calculation methods to almost try and find where these pinch points are on the system. So we're not talking about really every single transformer has monitoring. It's just we can see methods to actually detect across the grid where there could be harmonic heating. Now, if we are seeing harmonic heating, then an option is to derate the transformer. So that could be one if the utility doesn't want to replace a thing or save some money, just derate the thing. Another one is just to accept the higher rate of aging. Now, this is the higher rate is if a transformer has been fairly lowly loaded over its life, and there's really the paper is in a good condition, then it might not, if they're only expecting 50 years life out of it, then they might accept this higher rate of aging because the transformer will still last that long. Other things we can see here is maybe thermometers to monitor the tank's surface temperature. So what we like about this is just it's an easy retrofit. So that's the end of my presentation. Thanks very much for listening. And it's great to see everything else which is happening at TENCON. Bye.
Thank you very much, Dan, for that wonderful presentation. It's really interesting to see how high frequency harmonics we get from all this inverter-based technology is having an effect on our transformers and shortening the lifespan of them. It's certainly some food for thought for our electricity distributors. So right now, I think we need to take a bit of a break. I've been here a while and I need to go refresh my coffee cup. So we will take a 10-minute break and then we'll reconvene with the panel session. So thank you very much. Hello and welcome back, guys. So this is now moving on to the panel session of our workshop. So what I'll do is I'll introduce each one of our panel members, and I'll give them a few minutes to introduce themselves and pose some questions, and then we'll come back and open up the floor for discussion. So our first panel member is Dr. Bhavik he's the Technical Director of Oricon and Power Systems in Australia. So Bhavik, would you like to give us a little bit of a bio?
Yeah, hi, good morning, everyone. Hopefully everyone can see me and hear me well. So I'm Babak Badzadeh. I'm currently with Oricon Technical Director on Power Systems. My focus area is primarily power system modeling and analysis, looking at various aspects, including connecting generators, but also planning and operating power systems with very high share of inverter-based resources. I realize that the focus of this conference is, or this panel at least, on the a power system with a high share of DC connected inverters and converters. This topic that I have been following for more than a decade, basically, and obviously it's a very timely topic in Australia currently, and I'm sure that would be very soon coming to New Zealand if it's not already. And I'm very pleased to be in this panel. Thank you for having me.
Thank you very much, Robert. Our next panelist is Dr. Ram Adapa, and he is from EPRI in USA and is expert in HVDC and power electronics. So, Ram.
Yes, good morning. This is Ram Adapa from Electric Power Research Institute. I hope you can hear me and see me as well. I have been working in the power industry more than 3 decades. Of course, I started with HVDC with my PhD work, and then moved into different areas for system planning and operations and all that, and then came back to HVDC again with the integration of renewables with offshore wind and all that. HVDC is a key role it is playing nowadays, as you know. So that's all my expertise. I'm happy to participate today in the panel discussion.
Thank you very much, Ram. Our next panelist is Bernd Bonder, Group Manager for DC Microgrids, Fraunhofer Institute for Integrated Systems and Device Technology in Germany. Over to you.
Yeah, hello. Here's Bernd. I'm also a power electronic guy, and I've involved since 10 years in the DC microgrid development. So we've done a lot of different power converters for set kind of grids, and I'm also responsible for the grid we set up in 2014, which is since that date running without any big trouble. So we have around 7 years experience with a real running operation system, and have also developed a different kind of solutions for industry, as you maybe see with the DC industry project in the background, and also for other projects in data centers or in charging parks with 120 DC powered charging points.
Oh, thank you very much. everybody from all over the world here on this panel session, so it's really good to see. Bringing it back a bit closer to New Zealand, we have Dr. Hamish Laird from ELMG Digital Power. Hamish.
Thanks, Andrew. So we work in the integration of DC supply systems into the AC grid. We are seeing a huge interest in this from an industrial and power system integration point of view. We facilitate this by designing converters and designing the control systems. The key question I have about the future network, the future of the AC network, is that we at the moment have lots of rotational inertia in the system, and we seem to be removing it. And I'm wondering where that leads. And I'm also curious as to how we're going to manage that.
Thanks, Hamish. Yes, that is indeed a interesting question, and one that's going to require quite a lot of input. And then our last panelist is Tiffany Merritt from University of Victoria, Wellington, and he is representing our Vision Mataranga aspects of the project.
Tēnā koutou katoa, ruhini te maunga, ora o taua, nā te kauwhata te iwi, nā te tahuru waka nui te hapu, me nā ihu te whare tūpuna o Kāorangi te marae, nō reira ko tipinui tōku ingoa, e mihi nunui kia koutou i rongo te kaupapa o te wā. Greetings, thank you for having me. I used to work at Victoria University, but as of April this year, I'm now working at the University of Canterbury. Just a little bit of translation on how I introduce myself. I'm of Māori descent, so if you're not familiar with that, well, I'm one of the from the indigenous tribes of Aotearoa, New Zealand, and my primary tribe's kōwhata. So our ancestral mountain is Ruahine, and it's Ngala, North Island. Rivers Orowa, my tribe's kōwhata, my sub-tribe or hapu is Tahuru Wakanui. Our ancestral house is called Manaiuhu, and our meeting place is called Aorangi. So that's my way of introducing myself. Also, my mother's side, also in the Manawatu, I'm of the tribe of Rangitane. My father, who's also of Māori descent, I'm from the Bay of Islands, the far north, that's called Ngāpuhi, and also from the Bay of Plenty, which is Ngaitarangi. I'm not an engineer. My background's in law, but I've been in research management, including commercialisation, for about 11 years, doing that both in New Zealand and in Australia. And my current job, I enable researchers to try and give effect to the Vision Mataranga policies. So something that's unique about New Zealand is that when we apply for government funding, research funding, all applications are required to consider Māori interests. There may not be synergies or relationships or opportunities there, but they do need to consider them under the Vision Mataranga policy. And that's my job, to support and advise engineers and researchers to do that. So that's just a little bit of background from me. Kia ora.
Thank you very much, Tiffany. It's Vision Mataranga is a very important aspect to this project and all New Zealand government grants, really. So thank you very much for contributing to this panel. So now we're going to move to the panel session as a whole. So we'll open up the floor to questions. So anyone who's watching can send in a question. I think we've got chat options in both the YouTube stream and the Hover app. So feel free to pose some questions. There is a wee bit of a time lag between our live presentation and what actually shows up on this screen. So just bear in mind if I don't ask your question straight away. But in the interest of just kicking things off, we've got a few pre-prepared questions for our panelists. So Babak, what issues did you encounter with modeling a large AC system with numerous DC systems, i.e. wind turbines and later battery storage? when doing this as part of AEMO?
Okay, sure. So yeah, I guess what people might have seen from my bio, I was with AEMO for past 9 years before moving to Oregon earlier this year. So what we achieved over a 3-year period was to basically start from scratch and then develop the full system model in 2.5 years approximately. In my team, basically, it was all done in-house based on an electromagnetic transient simulation tool, as opposed to conventional power system analysis tools. One of the trigger, this is based on learnings over many years, like 10 years, and even like previous decade of my career before moving to Australia. But it was based on various learnings at the time, connecting some initiated by connecting remote isolated wind farms to very remote areas radially connected, and then a catalyst or accelerator for that, which was a good cause indeed, was the South Australian blackout in 2016, which essentially prior to that, it would have been considered impossible, but because of learning that electricity is an important commodity, or the most important commodity, essentially we were given the backing to start developing the models such that we can simulate correctly, accurately, and preemptively before such events can happen, and therefore we can put the correct mitigation measures in place, if you like, to avoid such phenomena to happen. Obviously, it's no secret that since then we have had a quite significant share of inverter-based resources. It has been growing quite significantly over the past 5 years. And then what we have realized is that even under some of the system normal conditions, we can't really accurately simulate the behavior of individual generators or the overall power system as a whole, as the share of inverter-based resources increases, and as at the same time, the two always coincide that if the share of inverter-based resources increases, then the number of online synchronous generators would also decrease, for which the conventional power system modeling and analysis tools have been there and have been accurate. So we know that. But as you get less of synchronous generators, more inverter-based resources, the accuracy would suffer. And for someone like AEMO that would need to plan and operate a power system, that's not acceptable. It has been obviously validated against the actual system event. I realized that was another question that you have put for me, so I would not be answering that in great detail here. But essentially, like in terms of challenges, one is that this is not an insignificant investment. Indeed, it's a very significant investment, and not many engineers can do that. I think what we've done and it can indeed happen, I want to highlight, is that you can basically train engineers up and develop all these. Like I said, bulk of it, almost 99%, was done in-house. But probably the key challenge is not just the time to develop, but time to use it, because we know that obviously they provide great accuracy, but at the same time, the speed of simulation is not something that someone can run the actual power system accordingly, because each simulation can take 1 or 2 or 3 hours basically to run. So this is still an ongoing challenge that is being looked at in Australia, and I'm sure across the world. And what the time it means indirectly, but quite significantly, is that the time to connect a new generator will also increase because of the time required and the skill required to conduct the simulation, analyze the results, and see if there is a problem that needs to be looked at in great detail. So these are some of the points I wanted to share, but I pause here, happy to build on anything or any aspect that I might not have addressed, but I'm keen to basically making sure that my also co-panelists have time to discuss. So I pause here.
Yeah, anyone else want to add to what Babak said about that?
Regarding modeling aspect, I would like to mention something. Again, the Ram Adapa here from EPRI from United States. In US, you might know we have the US network interconnected Eastern interconnect, Western interconnect, and then we also have Texas as ERCOT. The Western we call as WECC and Eastern interconnect. So, 3 separate independent AC systems connected by back-to-back DC ties. I would like to say the models have been developed for these big systems, all the interconnects connect separately for load flow and stability type models. When it comes to electromagnetic transients and a lot of power electronics and inverter-based, those kind of devices, right now the trend, of course, all around the world is what is called co-simulation. You can have a transient stability program integrated with an electromagnetic transients program where you simulate a lot of power electronics, switching and all that, and feed that back to a transient stability program. So these are becoming more popular these days, and standard models have been developed for HVDC and wind farms and all that. So a lot of work going on in North America as well, just supplementing what is going on in Australia with the AEMO. So let me stop there.
Oh, that's really interesting. Bern, you've performed a lot of work on DC microgrids. What are some of the issues and barriers around that?
Yeah, I would say one of the biggest challenges was the real setup. So we had done a lot of discussions before that with what architecture, what is the right architecture, with what kind of earthing we need, what voltage levels and stuff like that. So that was some work, but the main challenge was if we was finished with our discussions and started with setting up everything to find the right components to get systems running. We had a lot of issues with the installers. So if you go to say classic people who do the installation, we had a lot of discussions to teach them how to do, what is our idea, to get the understanding, so they do it. And also a big challenge was in the discussion about the safety in that grid. So if you set up a DC grid, you have to be quite good in safety analysis about electrical safety to overcome some technical issues in that field. It's doable. It's nowadays more easy than 7 years ago. 7 years ago, we almost has none equipment available. For example, all the converters we designed by our own because there was nothing available which we needed. Nowadays, it's quite easy, I would say. It's not as easy as an AC. AC, you can buy it from the shelf, but it's doable now, and you can set up a complete factory. Maybe we come to that later. Maybe in Germany we had set up a complete factory with 2 megawatt power level with DC, and it's a very big factory. It's the biggest factory from Mercedes-Benz. It's complete operated by a 500-meter DC bus in the heart of the factory.
Wow, that's pretty amazing.
It was a very tough work with over 40 companies. So we are working on that since 6 years now. So it was not done in AC in maybe 1 year or 2 years. It took much longer, but we learned a lot of things. And I'm also head of a standardization group in IEC, which has that topic as work package. So we try to write a standard to make it easier for other people.
Cool, thanks for that. I've actually got some questions from some of the audience here, so I'll try reading these out. So first one is by NASA from Auckland. I'm interested to know the tipping point in AEMO, European and American TSO, to shift to PSCAD and real-time modeling. RMS tools and Digilent, Syncel, and ETAP is currently used by New Zealand utilities. From your experience, when can they expect to shift to rigorous EMT type modeling? So that's open to anyone.
Okay, I can perhaps get started. I think it's a good question. It has been there for like 3 or 4 or 5 years, and as part of it, an international task force, if you like, we published a paper that is in IEEE Power and Energy magazine, November, December issue this year, and another one 2 years ago. And this question has always been there. So what is essentially meant by high or very high share of inverter-based resources? Initially started people saying 50%, but I think everyone knows now that is arbitrary. So it's really difficult to, substantiate as to what are those tipping points. Are there really breakpoints that from a certain threshold will make or break? What is very clear is that as it goes higher and higher, every single percent make it incrementally harder. For example, if you're talking about 80% to 100% or to 99%, I would say that would be much harder. One point, and I think Hamish was asking as a question, I would not be answering in great detail, but one thing I would like to set the scene is that imagine in 10 or 20 years, we have all achieved 100% inverter-based resources or renewable, especially in your context, because you have a lot of hydro, obviously. That would be a much easier system to plan and operate. I think the journey to get to that 100% is much harder rather than when we are at 100%. But in terms of answering the question more directly as to when a user or system operator or planner or TSO, ISO would need to consider moving to a different type of tool. And I would not say moving, because the RMS simulation or phasor domain would always have a place, but I think they are losing the confidence, if you like, for a wide range of studies. So they definitely need to be complemented by other types of analysis, such as electromagnetic transient. How I would go about it is that essentially one way is what the real power system performance tells us, what the testing of the actual equipment tells us. Do we get accurate results from using phasor domain simulation, or do we not? The other key point, which I think you have it under questions again, is that if we're looking at areas, especially small concentrated areas with high share of inverter-based resources, it's no secret. This has been there like for many, many years, decades actually. So power electronic interface devices, whatever type they are, DC, AC, DC, DC, AC, AC, whatever type they are, they tend to interact with each other. And that's another reason why someone would need to use EMT simulation on a larger scale to simulate power systems with high share of inverter-based resources. At the time that we started in Australia, the penetration level was about 20%. In some other states like South Australia, it could be 100% or 150%. And another point I would mention, and I would pause here, is that the percentage by itself is open for different definitions or interpretation, because one way you could say the instantaneous penetration, like for example, say right now, that could be like 100% or 100%. That's much easier to achieve as opposed to say, if we want to flat out achieve 80% or on annual average 80%, the implication of operating on sustained and ongoing basis is much more difficult compared to operating instantaneously. So these are some of the points I can share, but unfortunately it's a very good question. But this has been discussed, has been there, and we have been discussing among people that have been doing this for 1 or 2 decades. We could not really come up with a clean and nice number to say that above 50% or 60% is where going to make or break.
Yeah, that was a really good answer. I've got another question here from actually Ani Goli, one of our presenters earlier in the morning. He says, "Hi Boak, it looks like you use fairly extensive EMT models. How does one validate the models so that the results can be trusted?"
Good to meet you, Annie. I can't see you even, like I think after 2 years ago that I was in Winnipeg, and I mean, I should say, I think many of us probably here have learned things from, like, as undergraduate student, I've read what you've done, so obviously. But in terms of, I think it's a good question, and this is another good question, because one thing I would like to highlight is that, yes, EMT simulation is much more capable and flexible tool, but in the end, someone like I or you, an audience, basically develop these models, so they could be as good as someone can think of, or I've seen once or twice that it could be even less accurate than the corresponding phase or domain simulation. So it's really down to the user. To partly address the comment question that Annie is asking, is that it has been for past few years systematic approach by most manufacturers that try to use the actual control code that the inverter runs with and wrap around that and make the software understand that and use it without any interpretation. So a user, a developer like me or you, is not going to touch that. That would be a good way to make sure that it's not lost in translation. There is no manual or human error introduced. But even so, you know, all models are for different purposes. As to realistically, you can have a universal model that can cover anything and everything you would like to look into. That is unlikely. But and in terms of validation, how I would go about it, like I said, we've done this previously once or twice in Australia, that we apply real faults to the power system and then compare the measurement and simulation. Obviously, that's intrusive. It needs a lot of careful planning. And if something goes wrong, the consequences are quite drastic. So we are not doing that anymore. Trying to rely, especially these days, the global warming, what it means is that we are not short of credible and non-credible disturbances. They give us good opportunity to essentially verify the actual system response against those more extreme scenarios, and if any calibration needs to be made. The last point is that unfortunately it hasn't been done in Australia, and I'm sure not in New Zealand, but in countries like Germany or Spain, and to some extent in China. They have also established a laboratory for basically clean testing of like a wind turbine or inverter, that essentially you can subject the actual physical equipment against like hundreds and thousands of real tests and see how it behaves and whether that would be consistent with the model response or if the model need to be improved. So these are some of the few things that I can think of. Hopefully I answered this question adequately.
Yeah, I think you did. I'd like to see some of these labs. We can test whole wind turbines and things. It'd be quite impressive. If you got more questions from the audience, please put them through. But in the meantime, Hamish, you've had a lot of experience deploying large converter systems around the world. What are the key problems that you've encountered?
Well, I think just to touch on the same discussion, we've seen that the application of the next converter causes the problem. So when you've installed 6 and then you commission the 7th, then you realize that you have problems. So what we've come up with is a marginal model of converter stability, so that we find the 100% converters is simple, 60% converters is difficult, but when you move to 65%, it gets more difficult, or you get all of a sudden something unexpected. And it's always the unexpected that causes the problem. So what we've done is come up with frequency domain models for the marginal stability of the next converter in the installation. So that's the key thing that we see in building these out, is that it's the marginal application of the next converter that you need to be able to decide whether you're going to have a problem before you put it on or not. Issues you see is sometimes in large wind farms, they'll put up the 180th wind turbine, and then there'll be a 13.78 harmonic resonance, which trips the farm. And that's kind of embarrassing for the wind turbine vendor. The most interesting thing about that is that the wind turbine vendor has the people who designed that wind turbine don't seem to really have an appreciation of what marginal stability or stability changes with penetration of equipment means. The problem is further compounded by installing converters that are quite electrically close, but not on the same bus bar. So you have an AC network, which is theoretically strong in between each converter, but just weak enough that you end up with stability trouble. So there's a mixture of harmonic stability, which we don't really understand, because what we do is solve the problem rather than try and understand it completely before we solve it. But I think that that's the biggest issue that we see, is the marginal stability in installing things. And it's extremely annoying when you're commissioning power converters that you're putting in 15 and you can get 13 of them operating correctly, but the 14th one won't go.
Yeah, I can imagine that's pretty frustrating. Yeah. Tipanu, what is Mataranga Māori, and how does it fit into a world context?
Kia ora noa. So the literal translation of Mataranga Māori would be Māori knowledge or Indigenous knowledge, and then Māori way of knowing. I suppose to take that a bit further, it's how we understand ourselves in the environment and how we can exist in harmony with our environment. So it includes in-depth knowledge of native flora and fauna, and also our unique ways of communicating that knowledge, which include carvings and tattooing, song and dance. But it is also a repository of knowledge that's ongoing. When my English ancestors arrived in New Zealand, we didn't stop developing our culture, our knowledge, so it continues to be developed these days. And so where it can interact with science is if we look at sustainability, energy efficiency, and an environment that we'll pass on to our grandchildren in a better state than we've got it now, that's how those two can synergize. Another part of that is getting more Māori and Pacific Island people too, and other cultures into the engineering and sciences, so they can bring their cultural worldviews to that discipline of science. And just, I suppose, in terms of mātauranga, it's not what I'd call a property or intellectual property. It's a collective possession. So it's something that's used and developed, and there aren't owners, but there are guardians of what we call kaitaki. And one of their main aims is to look after the knowledge and to assure that knowledge benefits the collective and not the individual. For the latter part of your question, how would it interact with the international community, I think that was. I'd turn that question around a little bit, and I would ask, how could the international, say, science interact with mātauranga? I won't get too in depth into this, but because of colonisation and other things, we're still in the process of making sure that our mātauranga is able to have space in our homeland, and we're able to advance that. But we're also open to international opportunities as well. So I suppose once we return to our comfortable space in terms of mātauranga in Aotearoa, New Zealand, then I suppose we're in a much better position to see what that would look like internationally as well. So I hope that kind of answers your question.
Oh, that's a really good answer. Thank you for that. I've now got another couple of questions popped up in the feed. So Ani Gole says, thanks for your answer, Babak. In Manitoba Hydro, we very carefully validated the EMT models against the Nelson River HVDC system response, but it is a long duration job with many difficulties. So I'm not sure that's actually a question, just a comment. But here's another question. Matthias Brand, thanks Professor Jonas Lesters for the interesting control theory presentation. Would you be able to expand on the definition of passivity and where the requirements for passivity comes from, please? Thanks a lot, Matthias. Well, Jonas isn't actually on our panel, but does anyone want to have a go at answering what the definition of passivity is from Jonas's presentation earlier today?
I can have a stab, Andrew.
Yeah.
Okay, so passivity is the property of a system that the system always dissipates energy or does not have the ability to generate energy. So a passive system, when you interconnect them, the effect is that two passive systems connected together will be inherently stable. And it kind of goes to what Lyapunov was getting to when he came up with his stability proof that said that if you can have a function that you are always heading towards a stable equilibrium point, you will always effectively be dissipating energy. And it kind of goes to the existence of damping in a system, that the system has enough damping. So passive systems, if you look at their, so if you were to treat it as an output impedance, the output impedance would always be real, have some real component. So it could not, and that real component could never be negative. So, but passivity also exists in the large signal, not just the small signal. So it's really useful for system stability. It is one of my favorite nonlinear control things to deploy when everything is going wrong, I guess. It is extremely useful. Turn on the passivity. Right. Fantastic.
Awesome. Does anyone else want to contribute to that discussion? No? All right. Ram, can you share any insights on what you think are better circuit topologies for DC conveyance?
Yes, Andrew. Yes, I will answer that. But just for Hamish has raised an issue earlier about inertia. I want to say a few words on that and then come back to DC.
Yeah.
First of all, we are all looking at inertia. We are losing inertia because we are retiring the big power plants. We are getting the renewables. I mean, that's a fact for sure, no doubt about it. But what we are doing in North America right now is most of the utilities where they have synchronous generators, making them as synchronous condensers and still keep them in the system to provide that type of inertia that is needed, and also the voltage support and reactive power support and all that. So that's happening quite heavily to some extent compensate the inertia that is gone because of the generators are retired. So synchronous condensers are either new ones added or the existing generators converted to synchronous condensers. That's one aspect. The other thing in the broad way that people have been talking about is designing power electronic inverters to just run as grid forming inverters, and you really don't need to have physical inertia per se. So that research is going on, and I mean it is possible, but of course in a big scale, in a big power system, it is yet to be seen how successful power electronics can provide what they call synthetic inertia that is needed to run the power system at a regulated voltage and frequency. Okay, so those are my comments on the inertia side. Coming back to HVDC, of course, right now, as you might know, is the voltage source converter technology is really the one that is coming up in a big way with the modular multi-level converters. Because it's voltage source, it has a lot of advantages to integrate renewables both onshore and offshore, either wind or solar activity, any of those. So that is the one that's new topologies are also coming up, of course, for that. We're talking about maybe before the topologies, again, there is a challenge with the voltage source converters. We have We can have a DC grid with voltage source converters and all that, but really the challenge is the protection. DC circuit breakers are still, I mean, they are available now, but they're very expensive, and it's a lot of research needs to be done. Still, make sure hybrid breakers are economically feasible and all that to limit the fault currents, because when we have voltage source converters, voltage source just like a generator. So when you have a fault, you have very high fault current. Okay, that's a big challenge that is still being addressed by the researchers as well as the industry as a whole. So coming back to topologies in North America, what we are looking at is a macro HVDC grid on top of the existing AC 765 AC grid. This has been talked about, initiated by one of our system operators here called MISO, Midwest ISO. It was initiated there. The concept, as you may know, that we have a lot of offshore wind platforms, wind resources in the Midwest part of the United States. And the loads are all over in California, here in New York and Chicago and other places. So there are a lot of different topologies are talked about. DC grid, overlaying on top of the existing AC grid, but still it's in its infancy stage because we need to have a global organization to have that thing to happen. We are talking about it in a big way to see the infrastructure bill released by the President Biden here can assist in helping that kind of concept where we can have a global organization that could handle that kind of thing, because it may not have benefit to each and every state, and some states subject to that going through lines to their territory. So those are issues. So those are the topologies that we might see down the road where AC and DC working together. So in medium voltage also, we see a lot of work going on, converting existing AC corridors to DC to get extra capacity, and also taking generation, wind and solar to the load centers. So, okay, let me stop there and give the time to others.
Oh, it was really interesting. You just keep going.
Yes.
Yes. Bird, is a DC microgrid desirable over an AC microgrid? And if so, why?
Yeah, you ask a guy who works since 10 years with DC microgrid, so I think you know the answer. Yes, of course. I want to start with an example because it's maybe more physical to start with an example. As we set up a project with an industry partner, we commissioned the DC grid. We set up some machines, and then we had a blackout in the complete factory hall. And we was really afraid that we was the reason for that. But after a couple of minutes, we investigated that our system is still running. So it was not our fault. Everybody saw that it was not our fault. So it was really a nice experience and show that DC is able to run without AC. So it's no issue. The system was never designed to run without the connection to AC. Of course, it cannot run forever without AC. But the reason, for example, why that kind of industry partners want a DC grid is they want to be more independent from AC. For example, Mercedes needs up to, in that blackout scenario, our part of the DC factory was able to run, and we stopped every machine by hand and slowly. And so we had, for each machine, we had a stable stop position, and after the system was back again, we could run immediately. And the rest of the factories, it took up to 5 hours until they were able to start the production again. Because even if you have maybe 100 or 200 milliseconds blackout, for example, a welding process of a carrossery is in a not in a situation you can go on with your process. So you have to stop you have to repair set issues, and then you can go to a stable next point. That is one reason, for example, why DC is good, because you can make a quite easy operation even if you're in that kind of situation where AC is struggling. You can integrate batteries quite easy, PV and stuff like that. And in the industry area, we also included all the drives to the DC bus. So it was easy to use the braking energy if the motors are braking. All the energy is normally wasted. So you make a lot of heat in the factories. And after that, you need a lot of cooling energy to cool down the factories. And so we was gaining on two areas. We achieved less peak power level. So we reduced the peak power at the entrance point to the AC grid about 80%. So a very, very high gain here. And the second point was a lot of efficiency improvements, because we was able to reuse the braking energy. Yeah, and a lot of other things like less cable stuff, because we use higher voltage levels compared to AC. So it's not really at AC/DC. It's because of the higher voltage level, it's easier to achieve higher efficiency and lower currents in the cables. So we was able to save up to 30 to 50% of copper in the cables, and yeah, and many other things. But I think it's a good first overview about what is DC, why DC can be a benefit.
Yeah, definitely highlighting some great examples there. Definitely. I got another question from Ani. Dear Adapa, DC grids are being proposed all the time, but as you have said, circuit breakers may not have evolved sufficiently to be economical. Do you think AC systems with multiple DC infeeds may be a better solution?
Well, yes. Well, that has been going on already right now with multi-infeed DC with AC systems that is already there. But I think as you see now in China, for example, they have 4-terminal DC mesh grid has been already demonstrated at 500 kV level last year in 2020. They energized that system. So we will see that kind of system will expand to more terminals, and especially with the offshore wind, certainly that DC grids will become more and more rather than AC embedded with DC. Of course, on the mainland where we have most of it is AC system, yes, DC embedded here and there will be there. Certainly that is an opportunity, more DC systems embedded into the existing AC grid. But offshore wind platforms and new construction where we see, I think DC grid is going to be the new way of doing, integration to the rest of the mainland, main grid, offshore wind, especially they're talking about many DC grid projects. The DC breaker, yes, the hybrid breakers have been proposed by Chinese. The cost is still high, but with the volume and with technology improvements, I think the DC breaker cost will come down in the future. That's the expectations that I have. So I think the future will be a mix of AC and DC multi-infeed as well as DC grids as well. And when you gave me time, Andrew, I just want to mention one more hot topic that just got released today in US. Yep. This may be of interest to audience. Electric companies joined together to form a new National Electric Highway Coalition. This is a heart of the press topic. I'm just reading from the T&D magazine. They published it this morning. I got the news. What this is in US, we have many electric utilities, what we call investor-owned utilities. They have all joined with the electric Edison Electric Institute, EI, and formed a coalition to, just 1 second.
It's getting a call.
So it's a coalition to build an infrastructure, a national electric highway infrastructure that can provide charging stations so that people can use electric cars to travel long distances. As we know, the electric cars have limited mileage in terms of how much travel they can go, and then try to find a station to charge their car sometimes is hard. So to avoid that problem, to increase the penetration of electric vehicles, this is the coalition that they formed in a big way, and the government is also, DOE, the Department of Energy is involved, and a lot of funding going in. So this is the kind of infrastructure they are planning to build for charging stations. So I'm hoping similar to this coalition, things could happen for integrating renewables into the main grid, providing instead of charging stations here, there where they can just integrate the wind and solar power, and this might happen with maybe DC option as well, DC grids also. So things might happen, but I thought what I read is interesting, and maybe other countries may be interested to do this. Just to increase the use of electric vehicles. Okay.
This sounds really interesting. How many companies are involved in that?
Right now, they say 10 companies. It is in the TND World newsletter, but more and more are joining. And the idea is to all the way from New York to California, if somebody is planning to drive an electric vehicle with 200, 250 mile capacity with batteries and all, so they could be able to stop in the middle of nowhere. They could still have a station somewhere where they could charge. So this is the idea, is to develop the charging station, just like, highway next to the highways where they're driving these vehicles next to the highways, just follow the highway paths and put these enough number of stations that so that electric vehicles could be charged anywhere they would like to, just like we have gas stations now.
Yeah, it's a great idea.
Yes,
and that,
yes.
that sort of technology.
So similar things happen. Yeah.
Yeah, that
because there is a need for that, and there is. Sorry, we are overlapping. Go ahead, Andrew.
You go. You go.
There is a need for that kind of thing because we have, especially the present U.S. government, Democratic government, Joe Biden has put some restrictions on electric utilities not to generate, mostly renewable generation to go in the future, and retire some of the old coal power plants and all that. So one way of doing this is also the electric vehicles and charging stations and all that. And so just to avoid the problem of charging and all that. Of course, there is other side is research is going on to have fast charging, as well as also increasing the capacity of the battery that they can handle it within the car to get more mileage. And fast charging is a lot of research is going on in that area as well.
Yes, definitely lots of change afoot for the industry. I've got another question here from Tech Lee to Bernard. What do you think is the best control strategy for power sharing and voltage regulation on DC microgrid cluster?
Okay. So we used a troop control strategy. I think you heard already about that. This is a good way to do it. And in the industry project, I already mentioned several times. It was amazing that it is also working in a big scale of a factory. So they also use that. The tricky part is here to in that industry project to you have to find a consensus with all the partners. We have, I think, 5 inverter, motor drive inverter manufacturers. We had for the front end, I think 3 or 4 partners. So it was, I think, around 12 partners who've done power electronics, and we have to coordinate all the characteristics so that the complete system fits together. That is a little bit tricky, but if you can deal that, it's quite a very flexible solution. But since we always had some stability issues, so we have to do parallel simulations, and if you do it from the beginning on, you can make it run really well. Another strategy we already really done in practical projects was more easy in, for example, data centers. We have only one device who does the voltage regulations, and all other devices don't touch the voltage anymore. So you use them in current mode or something like that. But only one device makes the voltage control. So this is also doable. And in another strategy which is also working is, for example, in industry projects with not much converters, and if the converters are all from one manufacturer, you can do a kind of master controller which controls all the devices. But in our experience, that only works with maybe up to 10 or 15 converters. And if you go beyond that limit, it gets very complicated because all the communication stuff gets complicated. You have always at each point calculate the current balance, so that all the incoming and outgoing currents are equal, and that is quite tough if the number of inverters increase. This is really concepts I have practical experience with. In theory, there are more available, but this I can recommend for practical projects.
Well, thank
Hopefully
you for that.
That helps.
yeah, that's really good answers. I'm just conscious we've got about 4 minutes left of the session, and I do have one last question from Nihao, which was, what will be the future of plug-in hybrids compared to proper EVs? He's also interested in what is happening in Europe, I guess, around that topic as well. So that's open to everyone. The future of hybrids, plug-in hybrids compared to proper EVs. I suspect I'll have a go at answering this. I think plug-in hybrids are a stepping stone to full EVs, smaller capacities, a lot, probably less strain on infrastructure as the charging requirements are a lot less than a full EV. But is that what's happening in Europe, man?
Yeah, I can give some insights of Europe. In Europe, we go the way in the other direction, do more and more power. So I'm involved in the standardization of DC charging, and we started with maybe 50 kilowatt charging stations. Then there was a request for 350 and 500, and now we are just doing in a standardization project charging for trucks, where we go up to 1,500 volt and 2 megawatts, but it's not fixed now. But what I learned is that we thought 50 kilowatt is much high. It's very high power level at that time. Then we was able to do it. So now 350 was discussed, and we said, oh, 350, it's too much for a normal electric car. And now we're doing it for trucks. It's really a nightmare now, and it's really all the technical issues we have to overcome are increasing. So now we are discussing about a lot of safety issues, and it's not easy, but it seems to be physically possible. So we will do it. But I think it's really, really long discussion point. But so the point I want to figure out is that If something is possible, it will come. And yeah, this is my experience. I'm not sure what is your experience, but if there is a way, the industry try it out, and if there is a business case, it will stay. So, and for the electric cars, maybe it's a little bit, it's unclear. So we discussed 10 years ago, we discussed if it is feasible with electric cars. Now we're discussing about trucks. Yeah, I'm not sure what if it is useful. We also are involved in projects where we do not go the way with charging. We do the overline charging on driving. So we have overhead lines on the trucks, and say charging while they are driving on the highways. And if they leave the highways, they have a fully charged battery. But we have also there a lot of issues with if you have, for example, a mountain, a steep mountain, and a lot of trucks start, we have a jam, and also trucks have to start at that mountains. Says, your cable maybe is very, very, have a very high cross-section area. You need to overcome that issues and stuff like that. We have to discuss and to make it happen.
Wow, definitely interesting times ahead, I feel.
Yeah.
Yeah. All right, I think we have to probably draw this to a bit of a close. So I want to thank all of our panelists for some really great discussion. It's been super interesting. Lots of good questions, lots more questions that we need to figure out. We certainly don't have all the answers yet, but it's exciting times ahead, I feel. So I'd like to hand it back over to our chair of TENCON, Dr. Nirmal Mir, and he can give us some closing thanks.
Wow, that was about 3 hours now. It started at 9 o'clock today, New Zealand time, and then it's close to 11:50. We're stuck to time. I think there were more questions than we ever thought of, and hopefully, I just want to first this particular session has been supported by MBIE, Ministry of Business, Innovation and Employment. For those of you who joined late, this is a SSIF program which the government of New Zealand has invested in. This is one of the 4 flagships which they have invested in the middle of COVID year, that was last year, and it's a 7.5-year program. And this is strategic because what you have heard in the last, I counted the number of presentations, 10 presentations, right? And we started with Professor Ani Gole talking about, the RTDS and simulations and things like that. He goes about 3 decades back, and he has been to University of Canterbury. Well, I know him personally well, and he had been here as part of the Epicenter Fellow or something like that at the top of my head. I remember a few years ago, quite a few years ago. So he has deep connections here. Then we have had a presentation by Professor Frede Blabjerg. He's one of the most cited authors in the world in an exciting area. And again, he has very fond memories of New Zealand. And so you might have seen the technologies which you are looking at and the rich kind of architectures which are being looked at, which might be of relevance to WS2. Then, of course, we have 2 emerging researchers, WS3, Jonas Lestas, and Dan Martin, a practitioner. So after those pitches, we then went into a fantastic panel. I would like to acknowledge Andrew for keeping his Kiwi humor and working his way through the 20-second lag time frame. It might be a little bit disconcerting, especially because the 3 people who beamed, one was from California, the other was one from Germany, which is about, I think, 10:30. It's almost midnight for Bern. And Babak is from, of course, closer, from Melbourne or Sydney. So, and we had 2 local speakers as well, Hamish and Tiffany. Sorry, they couldn't get much chance because they were so engrossed in this international conversation which was happening. But what I wanted to convey there was the notion about capability building, which we have to do in the next 30 years, and it has to be represented. And I think the Vision Maturanga is a nice framework to tie, what our current state of affairs is and where we need to be as a globe and as a nation for the next 30 years or so, in forming that inclusive partnership as we go. But I really want to talk, this is a conference. In the parallel session, there's a lot of students doing presentation, fantastic presentation. Some of them could not join here, but this recording is going to be there. And a fan has supported this workshop. And I would like to acknowledge, as behalf of TENCON 2021 chair, I wear that hat, to thank FAN for supporting this conference and also having this workshop. I think it's a fantastic way to kind of engage these international people. I've already started getting a lot of emails saying this is one of the best panels they've seen, the kind of people they are trying to do, because we are really talking about a problem which we are trying to solve of 2050 right now as we speak. So I think we have achieved all the KPIs and things like that. So I think I was tracking the number of people. I think it was 45 people or something like that from all over the world. We would share some logistics associated with it. I also want to thank the industry people who have been, about 25 of them have joined from New Zealand to join here. And also, I think MBI were also invited to just say, hey, we had some troubled times to start it up, but we have all these connections and much more. So it's a great start for FAN. On behalf of TENCON chair and my committee, I would like to wish Professor Neville Watson, who is the science leader of this program, who heard at the start, to really get going, right, and to build the team. And also, I think I'm also part of it. So just to shout out to all the PhD students and things like that, electricity is back, right? So let us now not talk about Edison, Teslas, and all those things that was about 18th century or whatever it is. We are back again. What you're really seeing is just electricity. It's electricity everywhere, highway everywhere, this everywhere. Power system is up and running. All of you should take, high school students should take physics, maths, all that kind of stuff. If you're not interested in electricity, go to robotics, which is the next workshop, a plug for that. Look at some fantastic people. You should come to engineering. Engineering is much more broader now. It covers not only, it's almost like STEAM, science, technology, engineering, arts, management, and all that kind of stuff. We are all in the university system. The other message which I wanted to convey to New Zealand universities and things like that is just to know the breadth of electrical engineering. You should invest in electrical engineering. You should invest in these infrastructure. You might have heard some of the best worldwide people from Aalborg, from Manitoba. These are high net worth labs. So I think we would need more of these capital infrastructure. So if there is anyone on the government or the MBI watching, we need more money. We need more investment. This is not toys or anything like that, which you really talk about, but we are actually going to deliver a safe solution. If you want to get into DC, there's a lot of conversation about DC circuit breaker. I come from the protection background. That is the key enabling technology. And I think Ram did talk about the one in China, which is a 500 kV one. So wait and watch. These things are coming as we speak, as we try to move electrons at the speed of light, but much more, and fully renewables and things like that. Also, you might have noticed the breadth of the end-to-end. We covered from modeling all the way through to the German speaker talking about what they're doing with Benz and things like that. So we need to work together. So good shout out to everyone else. For all the conference attendees, I hope you enjoyed. And it's almost like 12, so I think this is the time for us to close right on time, and the recording will be available. So I would like to thank on behalf of TENCON and wish all the best for the FAN team in the future. So with that, what do they call? Kakiteano, right? And we'll catch up on the robotic session for the other people. Thank you.